All right, so in 9.2, we are going to talk about ellipses. So we'll write an equation of an ellipse in standard form. We'll use properties of ellipses to model and solve problems, and we'll find eccentricities of an ellipse. So for your formal definition of an ellipse, it's a set of all points in a plane, and the sum of whose distances from two distinct fixed points, which are your foci, is constant. So any two that you came up with. So if we picked another point here and we were to do the distance here plus the distance here, it would be the same as if you picked this point here and did this distance plus this distance the whole way around. So the line through the foci intersects the ellipse at 2 points called the vertices. So your vertex are on the major axis, which is your longer axis. And then the chord joining the vertices is called the major axis, and its midpoint is the center of the ellipse. The chord perpendicular to the major is the minor. So remember that the major is always the longer axis, and the minor is the shorter axis. So just kind of this visualization of how you have an ellipse. So if you had your two fixed points, your foci, and you connected a couple strings and a pencil, if you just were to go all the way around, you would end up with this ellipse. So your standard form, if you have a horizontal ellipse, which means it's the major axis is on the horizontal axis, then you have x minus h squared over a squared plus y minus k squared over b squared, and the ellipse will always equal 1. If the major axis is vertical, what happens is that your a squared goes under the y minus k squared. So wherever your a squared value is, if it's under the x, then it's a major axis is horizontal. If it's under the y, then the major axis is vertical. And the foci are always on the major axis, and the way that you find the c value, the foci, is you do a squared minus b squared. If the center's at the origin, then you don't have to worry about the h and the k in your equations. So these are just a couple pictures of what this would look like if you have your horizontal ellipse, right? It's stretched more horizontally, where remember this a value is underneath the x's. If you have a vertical ellipse, it's stretched more vertically, and the a value is under the y in your standard form. So in our first example, we have to find the standard equation of an ellipse, having foci at 0, 1, and 4, 1. So they've given us those points. This is your 0, 1, and your 4, 1. The major axis has a length of 6, and we know that the foci are on the major axis. So our major axis will go from here to here, and we know that that length is 6, as shown in the figure. And they tell us, so A is 3, and they give you that B is the square root of 5. So let's first start just by writing out that standard equation for a horizontal ellipse. So we'll have our x minus h squared, and it's horizontal, so over a squared, plus y minus k squared over b squared equals 1. We know that the center is at 2, 1, so that's your h and your k. So we could say x minus 2 squared over a squared. A is 3, so a squared is 9, plus y minus k squared, so k is 1, so y minus 1 squared, over b squared. If b is the square root of 5, then b squared is 5 equals 1. So in the next example, we're going to sketch an ellipse, which means we need to get it into that standard equation. So the first thing you need to do in this case is we need this 36 to equal 1. So when we have 4x squared plus y squared equals 36. In order for that to be 1, we have to divide everything by 36. So we get x squared over 9 plus y squared over 36 equals 1. And now for an ellipse, so in an ellipse, your A is always greater than your B. So in this case, when we have to decide is the 9 or the 36 our A squared, since 36 is bigger, 36 is going to be our A squared, and 9 is going to be our B squared, which means then that this is going to be a vertical ellipse. We have a center at 0, 0, since we are not subtracting any h's or k's from the y. And then our vertices are always on the major axis. So our vertices are going to be on our y-axis. And our vertices are 0 and plus or minus our a value. So in this case, our vertices are at 0 and plus or minus 6. And so if we're graphing this, we have our center at 0, 0. Our vertices are at 0, 6, so 1, 2, 3, 4, 5, 6, and 0, negative 6. Those are your vertices. And then this 9, these are your co-vertices. So those go on your x-axis, but again, that's your b squared. So your b is 3, so we would go over 3, and we would go to negative 3. And then if you connect these points, ellipses are always kind of tough to graph. I feel like you always end up with kind of a flat side on one of them. And if you graph it, then you end up with your ellipse. So here again is graphing an ellipse, but if you notice, we are not in the standard equation. And so we're going to have to complete the square to get this into that standard equation. So same kind of thing that we did with the circles and with the parabolas. And so if we get the x's together, we'll have x squared plus 6x. And then remember to that, we're going to add our b over 2 squared. And then we'll have plus 4y squared minus 8y. And we're going to add our b over 2, but we're going to hold off on that for a minute. And then we're going to say minus 9. So our x is set up since the leading coefficient is 1. So here we can say x squared plus 6x plus b over 2. So 6 halves squared, so plus 9. But what we have to do with the 4y is we actually have to factor out of 4. So that way our y has a 1. So we have y squared minus 2y plus, and now if we add b over 2, so if we add 2 over 2 squared, we're going to add 1 equals negative 9. Okay, something to think about here is here with the x we added 9, so we have to add 9. With the y, it seems like we added 1, but really we're multiplying that 1 by 4, so we actually added 4 to that side. And so now when we factor this, we get x plus 3 squared, right? Because x plus 6, x plus 9 factors into x plus 3 times x plus 3. And then we have plus 4 times y minus 1 squared equals 4. And so now to get that standard form of your ellipse, we have to divide everything by 4. And so we get x plus 3 squared over 4 plus y minus 1 squared, and it might help just to say over 1 equals 1. And so in this one, we have to graph it. So we'll use this box over here to graph it. So if we pull some stuff out here, we know that the center is at negative 3, 1. The bigger numbers under the x, so we know that the vertices are on the x-axis, So there'll be the plus or minus a comma 0. 4 is your a squared. So your vertices will be at plus or minus 2, 0. Right? 1 is your b squared. So your co-vertices are on the y-axis, so they'll be at 0 and plus or minus 1. And so if we were to graph this, so if we were to draw our axes in here, we need the center at negative 3, 1. So there's the center. Oh, the vertices aren't at 0 because the center wasn't at 0. Sorry, I made a mistake there. So your vertices are going to be plus or minus 2 from your center. So from your center then, if your center is at negative 3, we have to go 2 to the right and 2 to the left. So I'm going to take this off here. And so your vertices, if your center's at negative 3, 1, your vertices, we have to add 2 to that, so we'd be at negative 1, 1. We'd have to subtract 2, so we'd be at negative 5, 1. And same thing, our co-vertices, we're going to have to add and subtract 1 to the y-coordinate of the center. So our co-vertices will be at negative 3, 2, and negative 3, 0. So our co-vertices would be up here and down here, and then your ellipse would look like that. So on this equation, if you notice, it's the same as the equation we did here, x squared plus 4y squared plus 6x minus 8y plus 9. So if we take what we had here where it says find the center, vertices, and foci, we already did part of that. Remember, our equation was x plus 3 squared over 4 plus y minus 1 squared over 1 equals 1. And so if we have to find the center, right, we already said that the center was at negative 3, 1. The vertices are on the x-axis, so we have to take that a squared, which means we're going to add and subtract a to this x value. So if we added 2, we would be at negative 1, 1. And if we subtracted 2, we'd be at negative 5, 1. And then the foci, remember, has the equation c squared equals a squared minus b squared. So our c value, c squared, equals 4 minus 1, which means that c squared equals 3, or c equals plus or minus the square root of 3. And your foci are always on the major axis. So your foci are going to be on our x-axis. So this plus or minus root 3 is what we have to add to the x value of our center to figure out where those foci are. So for our foci, we'll have negative 3 plus root 3, 1 would be one foci, and negative 3 minus root 3, 1 would be where the other foci is. So in this next example, we'll look at an elliptical orbit, and it says the moon travels about the Earth in an elliptical orbit with Earth at one focus, as shown in the picture. The major and minor axes of the orbit have the lengths of 768,800 and 767,619 kilometers, respectively. So that's the whole length. So the 768,000 goes from this end to this end, which means if we were to find, that's your whole major axis, so that would be then that 2a would equal 768,800. Or it would mean then that a, which would be the distance just from the center to one vertice, so a would equal 384,400. We could look at the same thing for B. We know that 2B is 767,640, right? Which means that 1B would just go from here to here, would be 383,820.5. And so since the Earth is at a focus, what we need to do is find our C value. So remember that C squared equals A squared minus B squared. And so if we use those values, we could say then that C equals the square root of A squared minus B squared, which would be the square root of your 384,400 squared minus 383,820.5 squared. So we get that C is about 21,099 kilometers. So what we know then is the distance from the center to the Earth. That's that 21,000. So if we want to find the farthest distance that the moon is from the Earth, that's going to be when the moon is way over here. So the greater distance, so the greatest distance is going to be our A value, right? Because just from here to here was your A value. So we're going to have our A value plus our C value. And if we do A plus C, we get about 405,499 kilometers. And then our least distance would be when the moon is over here. And so the least distance would be A minus C, which would get us 363,301 kilometers. And then the last thing with ellipses we need to talk about is the eccentricity. So it says that one of the reasons it was difficult for early astronomers to detect that orbits of planets were ellipses is that the foci of the planetary orbits were relatively close to the centers. So they looked almost circular. And remember, when we just did this last example, those A and B values, when you look at those two A and B values, they're really close to each other in terms of being circles, but they're just a little bit off, which makes it more of an ellipse. So to measure the ovalness of an ellipse, you can use the concept of eccentricity. So eccentricity of an ellipse is C over A. And so if you do C over A, so every ellipse will be between 0 and 1. And so what you find is that the closer the eccentricity is to 0, this will be more circular. And if it's closer to 1, it will be really stretched out. It won't look like a circle at all. It'll be really flattened. So if you just did your C over A, even without graphing it, you could get an idea of how the ellipse might look just based on what that eccentricity equals.